All right, this is 2012 APCalcBC BC, question number 6, yet again, another Taylor series. And if you watch the first two, the 2014 and 2013 video, you kind of see there's quite a variety of ways they can ask this question. And then this gives you yet another example of how they can kind of take this in different directions. There's certain similarities, but there's other things they can emphasize in this. And I think that's true of this question from 2012, where what they're looking for is different than 13 and 14. Again, a lot of it's straightforward, though, that we can definitely handle. Some subtleties, it'd be hard to get a 9 on this, but not hard to get 3 or 4 or 5 or 6 or 7 or 8 points on a question like this. Okay, so let's read this one. The function g has derivatives of all orders. Again, like in the past questions, that's just letting us know, hey, this question makes sense. And the Maclaurin series, we know they made this at 0, which we can tell because look, it's x cubed, x to the 5th. They didn't, it's not x minus 1 squared, x minus 1 to the 3rd. So that looks good. Maclaurin series for g is this. All right, we read the 3 parts. Using the ratio test, determine the interval of convergence, and immediately thinking, uh-oh, don't forget to check the endpoints. We've got that. Then we've got part B and a part C. And it turns out if we read a little closer, B and C are going to be very quick and easy. So I'd like to show you those 2 parts first, and we'll come back and get part A. And B and C don't depend on A at all. So we'd be okay just jumping right away. It depends a little bit, but nothing that's significant for us. So let's jump right to part B. I'm just going to scroll this a little bit further, and let's jump right to part B. All right, so we've got this. The Maclaurin series for G, evaluated at x equals 1/2, is an alternating series. And we can see up here, positive, negative, positive. Or you can see right here, we knew this was an alternating series. And terms decrease in absolute value to 0. So they're kind of helping us here is an alternating series. It decreases to 0. That's the alternating series test. They just stated it for us, which means it converges. So they're just kind of tell us, hey, it's going to make sense to ask the question that they're asking here. The approximation for g of 1/2 using the first 2 non-zero terms. Let's come back up here and see. What did they do? The first 2 non-zero terms, right there. They use that, and they put in a half. We don't have to figure that out because they told us the answer. They put in a half. They got 17 over 120. Show that this approximation differs from g of 1/2. So the real answer, if you had the infinite series, show it differs from the real answer by less than 1/200th. All right, what is part B asking for? It's asking for the error. So what's the difference between your approximation and the real answer? All right, for an alternating series, the error is really simple. The error is the absolute value of the next term. And it's just that simple. So come back up here. We saw they did the first 2 terms. What are you interested in? You are interested in the next term. So we are interested in x to the 5th over 7. So x to the 5th over 7. Wait, what was x? Oh yeah, they're finding this at a half. So it's 1/2 to the 5th power all over 7. And that's it. You are done. You could evaluate it, and let's see, 2 to the 5th is 32. And 32 over 7, 7 is like 7 over 1. I'll get 1 over 224 if you like to simplify. And sure enough, that's less than 1 over 200. That is it. They're just checking. Did you know what the error was for an alternating series? And the answer is right there. The error is the absolute value of the next term. Done. All right, let's do part B. I'm sorry, that was part B. Let's do part C. The first 3 non-zero terms, the general term for the derivative. Not too bad. Let's erase up here. So clean this out a little bit. And let's get part C. All right. They want the derivatives. X over 3, I've got that derivative. 1/3. So I'll just call this g prime of x. I'll say approximate because I'm not going to write the whole infinite series. The first derivative, x over 3, is 1/3. And I've got a minus. I take the derivative, 3x squared over 5. And the next derivative plus 5x to the 4th all over 7. Not bad at all. Okay, we've got that. Don't forget they want the general term. So come back over here and let's take this derivative. Good thing is, negative 1 to the n, constant. 2n plus 3 is a constant. So I go plus, plus, I've got that negative 1 to the n, constant, 2n plus 3, constant. And now let's take the derivative right there, x to the 2n plus 1. I'll bring down the power, 2n plus 1, and it's x, take off 1, x to the 2n. And that would be my general term. And that takes care of part C. So I've got my first 3 non-zero terms, and I've got my general term. Okay, not too bad at all. Now let's go up, and if you're looking at the scoring guide in this, it's a 9-point question. There are always 9-point questions. This got us 4 of the 9 points. So most of the points actually come in the first part, which we'll hit now. But even 4 out of 9 is not bad on a question like this. All right, let's go back up and do the first part. Let's clean everything off here so we have a clean screen to work with. Let's see here. Close enough. Oops, now it's close enough. All right, let's get part C, or I'm sorry, let's get part A, using the ratio test. So very transparent. Think, oh, that's easy enough. They're telling us because, as you'll find out when we're doing this problem, it's kind of a difficult ratio test to do. So at least they were nice telling us to do the ratio test. And there's a couple of little tricks in this one, or at least, yeah, 2 for sure. So ratio test. Let's take the limit as n goes to infinity. Let's put in n plus 1. I've got this negative 1 to the n plus 1. And I mentioned in a previous video, if you have negative 1s and you're doing the ratio test, you can just ignore them. I'll write it in here, but if you didn't write in the negative 1, it'd be okay too. I've got x. And again, I'm putting in for n. I'm putting in n plus 1. I take it times 2. I add on 1. I get x to the 2n plus 3. And on the bottom, again, I put in an n plus 1. So I get 2n plus 5. And we'll take that times a reciprocal. I've got a 2n plus 3. I've got this negative 1 to the n, which again we don't really need. I've got an x to the 2n plus 1. All right, the good old ratio test. What can we cross out? And now let's scroll so we just have a nice clean screen here. We'll come back to the question if we need it. All right, what can we cross out? As mentioned before, those negative 1s to the n we don't need. You could argue there's still a negative 1 left over. We would argue it's inside an absolute value. You don't need it. The x's, cross those out. There's 2 more x's on the top. So that's an x squared. So we're left with an x squared and a 2n plus 3 over 2n plus 5. We use L'Hopital's on this. We're going to get from the top, that goes to infinity. The bottom, that goes to infinity. L'Hopital's, we take the derivative. We get 2 over 2, which is 1, which leaves us with just this right here, the absolute value of x squared. Okay, we're doing the ratio test. We know that should be less than 1. So let's continue over here. The absolute value of x squared is less than 1. What we would typically do is we would put our absolute value in between negative 1 and 1. The little detail on this one is, well, wait a minute. I'm squaring a number, x squared. Isn't that always positive? So it's kind of silly to say it's bigger than negative 1. I could really say it's greater than or equal to 0. So I've got, x squared is it's going to be greater or equal to 0 over here, and it's less than 1. I will take the square root, and the square root of 1 is plus or minus 1. So it turns out x ends up in between negative 1 and 1. Because here, the square root of 1 is plus or minus 1. And guys, I'm getting my interval. I have to check the endpoints now, but I'm getting there. All right, let's check the two endpoints. We'll scroll back up and remind ourselves of the question. Let's check first x equals 1. Come back up. What was the question? Way back up here. Get those numbers out of the way. And so I am going to sub in for x a 1. Oh, that'll be easy. All right, see if you remember all this stuff as we come back down here. So I've got the summation, -1 to the n. I have 1, and the bottom was 2n plus 3. And the top was that 1 to the 2n plus 1. It doesn't matter because 1 to any power is 1. So I really have the summation, -1 to the n, all over 1 over 2n plus 3. Let me just scroll up so I don't have any minor errors in here. It's certainly the right. We've done that perfectly. All right. Look at that series. Guys, that's an alternating series. We've got the -1 to the n. Makes it alternate. So let's check. Does it really alternate? Yes, it does. Is it decreasing? Yes, it is. As you increase n, the denominator gets larger, your fraction gets smaller. What happens as we go to infinity, to the nth term? Well, as we go to infinity, 1 over 2n plus 3 goes to 0. So this converges. So we come back to our interval, and we include that 1. All right, not too bad. Let's get the last endpoint. Let's get the -1. And just to save us a little bit, let's just, I'm going to erase this. And let's call this x equals -1. Let's do it in a different color, so if you're kind of confused, hopefully you won't be. That'll be x equals -1. What would that change? Not too much. That wouldn't change. That wouldn't change. And then right up here in the top, I end up, we'll keep the fraction there, I end up with a -1 to the 2n plus 1 all over. And now let's erase this last part here, and let's work through this part and see what happens. And here's a little bit of a trick, and I could see somebody goofing this up a little bit. Not a lot of harm done. It cost you a point. All right, let's keep this. We have summation, -1 to the n. We have on the bottom 2n plus 3. And now we have to think about this 2n plus 1. Give me any integer. So we're thinking about 2n plus 1. Give me any integer. Take it times 2. Wouldn't that make that even? 2 times any integer would be even. Add on 1. Won't this be odd every single time? Try different values. What if n is 5? I get 11. What if n is 3? I get 7. So for any integer value, when you put it into 2n plus 1, you get out an odd number. So I basically, -1 to the 2n plus 1, 2n plus 1, I have -1 to an odd power, which is -1. It's not -1 to the n, not -1 to the 2n plus 1, it's just -1. -1 to an odd power is -1. So that makes this an alternating series again, and it would be identical to x equals 1. It would converge. And so our complete interval of convergence goes from -1 to 1, including both endpoints. And that's a really tricky endpoint test. You'd have to show your work for both. I did before I erased the one. On the real test, you wouldn't erase. And that takes care of this question. So hopefully B and C, like I say, hey, those weren't bad. A lot of A isn't too bad. And again, you can kind of look closer at those endpoints and see if those work out okay too. That completes 2012 BC Calc question number 6, our final of the 3 Taylor series questions.